Hey, welcome back. It's me again. Today we'll talk about digital signatures in their theoretical definition and in practice. So the scenario we're looking at is we have Alice and Bob as usual. Bob generates a signature key pair, a public key and a secret key. Then somehow he publishes his public key, for example, by sending it to some key database that's publicly accessible. And then everyone will be able to download Bob's public key. Then what Bob can do is basically send messages and generate signatures for them. So he would send message signature pairs over to, for example, Alice. Alice would be able to retrieve the public key of Bob if she doesn't already know it from the public key database, and then would be able to verify that the message that was sent was actually signed by Bob. In particular, Eve may also be like looking at the wire and seeing the message and the signature. And additionally, she of course also has access to this public database of keys, so she knows Bob's public key too. But all of this shouldn't help her like convince Alice that some message that actually originated with Eve was sent by Bob. And the security game for this is actually very, very similar to the one that we had for MAC unforgeability. So for message authentication codes, the kind of the symmetric version of digital signatures. The only difference is that now, of course, when we generate a key, then we get actually a key pair, a secret key and a public key. And in contrast to the MAC game, we now give the public key to the adversary, which makes sense because, like in reality, the adversary would also have access to it. And then the rest is as usual. So the adversary may ask for signatures on messages of his choice, and he can choose them adaptively. And then in the end, he outputs a forgery, or like a candidate forgery, M and sigma. And he wins if M is not one of the messages that he has queried, because then it's easy to find a signature for it. Just use the one that was provided. And the signature must be valid, obviously. So let's talk about this definition a little bit and go a little bit closer to like practical applications of digital signatures. In particular, I want to talk about this key database here. So for digital signatures, we always have this idea that if I generate a public key, I can just publish it to everyone and everyone just magically knows what my public key is. In practice, of course, that doesn't really work this way. So my question is, how do you get someone's public key in practice? And it turns out, yes, this kind of key server that we've seen before is actually something that's happening. I call this the PGP style. So pretty good privacy is the thing that's used for emails and such. And there the idea is basically, if I want to know your secret key, you would just send it to me over some insecure connection. And then afterwards, I would ask you, like personally, whether this is actually your secret key. So you send me your public key, and then for example, I could call you via phone, make sure that's actually you, and then make sure that the public key that I received is actually the one that you wanted me to send to me. There's a little bit more to this PGP style, but I'll get to this later. But mostly, like, this is the idea. You send me the public key, and I kind of, through a second channel, make sure that it's actually yours. But obviously, this is not very practical. If I, for example, visit a new website, I don't want to like have to confirm their public key through a third channel. Instead, what's used much more, I'd say, is that basically the person or the server just sends me the public key as before. But then additionally, it sends me a certificate. It's basically saying, yes, this public key is the one that belongs to this server or this person. So I guess the only question is, what does this certificate look like? So how can I certify this? Thankfully, digital signatures are exactly the right tool for this. So let's say I know some trusted authority and I know their public key somehow. Okay. The idea is that there are only few trusted authorities, so only need to know a few keys instead of like every key of every server in the internet. And then this trusted authority would basically sign statements in the form of like the PK Bob, so let's say it's a huge list of numbers, is actually Bob's public key. So that's the statement that would basically be signed by the trust authority. And I would get a signature sigma. I call this thing sigma cert, so that's the certificate for Bob. And now basically what Bob can do is just take the certificate and then just send the public key of Bob. So he just sends his own public key to me in addition to the certificate. And now I need to be able to check whether this public key that Bob sends to me here, if that's actually Bob's, or if this is like Eve trying to sell me a different public key, just pretending it's Bob. And well, I can check it by just checking the certificate here. So this way, if I go to some new website and they have a certificate by an authority that I'm trusting, then they can just send me their public key, which I maybe haven't seen before, but I can easily check that it's actually theirs, because it will be certified by the trusted authority and I can check their certificate. And just for the record, for PGP, there's also something like this. It's called a web of trust, where the idea is that if this is me and this is Bob, I may not know Bob's public key and I may have no ability to verify it directly, but I may know Alice's public key and I trust Alice, for example. Then if Alice kind of signs the statement that the trusted authority would sign for Bob, then I would be able to trust Alice and I would be able to accept Bob's public key through this. So it's basically the same principle, just that the trusted authorities are not like distinct parties that are trusted authorities, but I can just use any of my acquaintances for those. And this brings us to the question, where are signatures used in practice? And like the first kind of obvious example is email, where we have exactly this idea that we have Alice and Bob and they want to exchange messages and they want to make sure that the messages they send are actually authentic. So they are sent by the person who claims to send them. There are two technologies for this, which mostly differ in the way that they handle keys. We have PGP, which is kind of more like an anarchy thing, where most of the key handling is burdened to the user. So essentially, if I get a PGP key, I need to somehow verify that this is actually the correct key. If I'm not by any chance lucky that kind of this key is already in my web of trust somehow, I leave the details out here. But in general, this is kind of the idea where you either call the person and verify, or you have like these signing parties where other people kind of sign your public key so that you will be trusted by more people, etc. But on the positive side, there are no trusted authorities in PGP. Everyone can exactly choose which people to trust and which public keys to trust. The other approach is SMIME, which is more based on this idea of having trusted authorities and having certificates for your keys. So for example, for SMIME, if I get an email from Fabian, I basically get the notice here that this was actually signed by him. And if I take a closer look what's happening behind the scenes, then I can here see Fabian's certificate, which was issued by the DFN. And I can also see his public key, which is this RSA public key. Now the interesting thing is I don't actually even trust directly the DFN, so the Deutsches Forschungsnetzwerk. I'm only trusting them because there's like a chain of certificates that I'm trusting. So in the end, I'm actually trusting this certificate, which is the so-called root certificate. And this is one of the certificates that came like preloaded with my operating system. So essentially operating systems, browser vendors, etc., they all make a kind of pick list of trustworthy authorities. You have to fulfill somewhat strict criteria for these. And then basically those ship with my operating system or my browser, etc. By default, they're just trust. So I could go into my system settings and untrust them, but like by default, they're trusted. And then they actually signed the public key of the DFN. And then the DFN signed the public key of like a smaller subdivision of the DFN. And then the DFN signed the public key of Fabian. And through this chain of like my machine trusts this certificate, and they signed this certificate, and they signed this certificate, and then they signed this public key of Fabian, I can be reasonably somewhat sure that this is actually Fabian's public key. Oftentimes, these certificates are something that you have to pay for. So you have to usually pay some trusted authority so that they can actually do the checks to make sure that you are you and they are signing the correct public key. But then you would get the certificate and you can essentially use it to send along emails like it happened here. So back to our overview. where are signatures used too? So emails was kind of the obvious thing, right? But one that's much more impactful, I'd say, in practice is that like every single HTTPS call that is happening, and those are a lot, they are all involving digital signatures to make sure that if I do an HTTPS call to some server, that actually the answer that I get back was actually originating from this server and isn't something that like man in the middle, like Eve or something, would try to make me believe that this website says something. So there, the obvious thing is HTTPS calls happen a lot in web browsers. So we can also take a look at this. So let's say, for example, I go to paul.uppd, and I want to make sure that like the grades that are shown to me are actually the ones that Paul thinks I have. And there's not some man in the middle or anything. So for this, kind of the same mechanism as for smime happens. So if I take a closer look at what's happening here, then I see that this is an encrypted connection, and I also get to see like the certificate of Paul. And this is something that my browser just checks in the background. And again, we have like this indirect path, so I'm not actually trusting Paul directly because it's like a random website. But I'm trusting this root certificate. They trust these guys, they trust these guys, and then they certify that this is the correct public key for Paul. You can also check something else like Google. If I go to google.com, then I also maybe want to make sure that they are who they say they are. And then yeah, this is their certificate. And all of this is just to make sure essentially that if Google sends me a public key saying, hey, this is Google's public key, I can actually verify this using the certificate chain and their certificate that they send alongside. So this is what's happening in web browsers. One of the nice things of HTTP calls is that today they're like everywhere. So I guess a lot of apps, for example, they just do REST calls to some server, which are basically just HTTPS calls. Most of the apps in this apps ecosystem, most of the calls that are happening in JavaScript, all of this, they also use HTTPS, and by extension, all of the data that they're sending is authenticated. One really critical area are actually where digital signatures are used are operating system and application updates. So we all know this, we get updates for apps and our operating system regularly. And the idea is now that these updates that I get, they would be signed by the operating system vendor, so by Microsoft, for example, for Windows updates, or by the application developer. And essentially this makes sure that you don't just get pushed an update which you did verify the origin from, that would, for example, install a keylogger into your operating system, which you would never be able to detect. But because these updates are signed, like your update process would reject all updates that were kind of written by a third party and not by let's say, Microsoft. There's a bunch of signature stuff going on in cryptocurrencies. Because the whole idea of cryptocurrencies is that if I have a coin, I can basically create a digital signature on the message, I give this coin to this public key, and then this public key would be a public key of some other person. And then I just publish this signature. And then there's a bunch of blockchain stuff going on usually to make sure that I can't do this twice, etc. But like at the core, it's kind of a chain of this coin belongs to this public key. And then for this public key, there's a signature on a message that says this coin is now given to this other public key. And then this public key can again extend this chain and basically say I'm giving this to this third public key, etc. Okay, and then there are a bunch of other use cases. For example, if you're using Eduroam at the Paderborn University, you had to download a certificate to allow you to access these. And there's also like a German identity card, or if you've ever done taxes in Germany, you may know Elster, where you also can identify with like a certificate, etc. So this was a quick rundown of signatures in like a more practical context. I guess I'll see you in the next video.